Microphone.
Okay.
Let's begin.
Yes.
Okay, so dear colleagues, let me open our meeting. So we have a dissertation for the educational program 8D05401 Mathematics at the SD University. On the agenda we have the defense by Yerkin Shaimerden of dissertation titled Cylindrical and Subelliptic Sobolev-Hardy Inequalities. And the research was prepared at the Department of Mathematics at Natural Sciences of the SD University and the Department of Mathematics of Ghent University. Form of defense dissertation. And this dissertation is presented the first time. So this is the first defense. And the working language is English. Okay. So we have permanent members of our council here at SDU, me, Nurlan Berbekov, the chairman, next Nurlan Ismailov, next Shirali Kadyrov, and Gauhar Arepova. And we have also temporary invited members, and they are Bart de Brun from Ghent, Muhammad Asad Zaignum, sorry, from Aktobe University, and Agirim Kalabay from Kimet. Okay. So all 7 members are present here. Some are online. Nurlan Ismailov and Shirali Kadyrov are participating online. Also, Muhammad Asad Zainum participating, and Agirim Kalabay. Also Bart Dobrin also is online. So we have a quorum established, 7 of 7, and we can begin. So we must vote. So we must vote open by hands for this agenda. I think.
You mean we must vote for starting the defense?
Yes.
Okay.
Okay. Everyone is for this agenda. It is approved, and also I must present supervisors. Local supervisor is Iserginov Nurgisa, and the foreign supervisor is Mikhail Ruzhansky from Ghent. Also, we have 2 official reviewers, Futoshi Takahashi from Osaka and Mesky Alexander from Kutaisi. Okay, so I give it's your turn. So our secretary.
Now characteristic of doctoral student. Yerkin Yerbulatovich Shaimerdenov was born in Kızılorda. He received his bachelor's degree in mathematics from Süleyman Demirel University in 2009 and his master's degree in mathematics education from Semipalatinsk State Pedagogical Institute in 2012. He is currently a joint PhD candidate in mathematics at SD University Kazakhstan, and Ghent University, Belgium. His doctoral dissertation is entitled Cylindrical and Subelliptic Sobolev-Hardy Types Inequalities and is devoted to functional inequalities and related problems in mathematical analysis. Yerkin Shaimerdenov began his professional career as a mathematics teacher at secondary school. He subsequently gained extensive experience in education and university administration. He later served as director of the rector's office at SDU University. Since 2023, he has been working as a senior lecturer in the Department of Mathematics and Natural Sciences at SDU University. He is also engaged in research activities at the Institute of Mathematics and Mathematical Modeling in Almaty. During his doctoral studies, he undertook research visits to Ghent University, Osaka Metropolitan University, Hiroshima University, Istanbul Ticaret University, Tsinghua University, and Paris Nanterre University. He has presented his research at numerous international conferences, seminars, workshops, and summer schools. He is the author of author of 4 published scientific works in international journals and conference proceedings, as well as 3 research preprints. His publications concern critical Sobolev type identities and inequalities, cylindrical critical Hardy type inequalities, Sobolev-Hardy inequalities, and functional inequalities on stratified and homogeneous Lie groups. Yerkin Shaimerdenov has participated in a research project funded by Ministry of Science and Higher Education of Republic Kazakhstan. From 2022 and 2024, he was a member of the research group for the project entitled Magnetic Functional Inequalities. From 2024 to 2026, he has been a member of the scientific project entitled Cylindrical and Hyperelliptic Functional Inequalities. Recently, he was awarded a Jas Ghalem postdoctoral research grant for young scholars for the project entitled Sharp Remainder Term Analysis for General Weighted Cylindrical and Subelliptic Functional Inequalities. He has also received research visit and travel grants from Ghent University, the University of Connecticut, and other international academic programs. Yerkin Shaimerdenov is married and has 3 children. It's all.
Okay, thank you. Other questions to our secretary? Okay, no.
Okay.
And,
So,
oh,
okay. So I think, okay, can you hear me?
yeah.
Okay. So I will, my name is Bart de Bruin. I'm chair of the program committee of mathematics at Ghent University. As you know, this was a joint PhD between SDU and Ghent University. And so I will moderate the subsequent public stages of the defense, including the candidates' presentations, the question and answers part, the presentation of the scientific consultants and official reviewers' reports, the general public discussion, and the candidates' concluding statement. Can I ask the candidate, Mr. Yerkin Shaimerdenov, to give a presentation of the work you have done during your PhD?
Okay, thank you, Professor. Let me share the screen. So I think it's visible, yeah. You can hear me, yeah?
Yes, we can hear you.
Okay.
Okay, then let me start my presentation. Actually, my dissertation consists all these chapters. The first 2 chapters is the introduction and preliminaries. So I'm going to speak about the given information in the introduction, that thus It's about reviewing of the classical inequalities. Then in the chapter 3, we have Sobolev-Hardy inequalities in cylindrical setting. So mainly, I will present the main results in the chapter 3, and in the chapter 4, we give the analog of the Sobolev-Hardy type inequalities from chapter 3 on the stratified Lie groups. In the chapter 5, we give the analog of the previous results on the homogeneous Lie groups. So mainly, I will focus, give information about the inequalities that are from the chapter 3, then shortly explain how we get the analogs of them in the stratified groups and the homogeneous Lie groups. In the chapter 6, we have applications of our previous results, and then the chapter 7 is for conclusion, and then the last one is references. So let me start from the reviewing, recalling the classical results. The first one is the Sobolev inequality. It's the inequality of the LP norm of the U is bounded from above with the LQ norm of the gradient of the U. This is the classical Sobolev inequality, where the constant is known explicitly and attained. The sharpness of the constant was shown in the works of the Albin and Talenti, and thus the extremal function is called the Albin-Talenti profile. The next one is the Sobolev type inequality. In the work here, authors show that whenever we replace the gradient of the Sobolev inequality, the scaling argument forces the LQ in here to be equal to P. So we get this kind of sharp inequality, and they call it Sobolev type inequality. In their work, they show in L2 case equivalence of this inequality with the Hardy inequality. In the second work, also they prove the same inequality, and also they prove that this inequality implies the LP Hardy inequality. The next, we have the Hardy inequality. Hardy inequality was introduced by Hardy in the 1920-1925 in his several works. First, he presents the one-dimensional integral version, where the constant again is sharp, and also he presents its discrete version, where we have this inequality with the sharp constant again. Later, the multidimensional version will be given in the several other works. First, it was mentioned implicitly in the work of the Leray, where he studies the Navier-Stokes equation, but he doesn't mention the sharpness of the constant. Sharpness of the constant will be shown later. Here we have the improved Hardy inequality, where we have this kind of radial derivative. If we use the Cauchy-Schwarz inequality, we get the classical Hardy inequality. Thus, this inequality is the improvement of the Hardy inequality. In here, the constant of the Hardy inequality is sharp and unattainable, meaning we don't have the function from our space, solar space, that equalizes this inequality. This inequality is also the scaling invariant. Under this scaling, as this one doesn't have extremal function, we have this kind of function which is called the virtual extremizer. This function doesn't belong to the for this space, but this one satisfies the satisfies the associated Euler-Lagrange equation as a distributional solution. Here, this one LP this is the P Laplacian. The next, we have the supercritical case. The previous one was the subcritical, where the P is less than n. In the next supercritical case, P is bigger than n. So when the P is bigger than n, then the exponent of the modulo x is bigger than dimension. That means there is a singularity, meaning the LP norm diverges. To correct that, to control that, there is several ways. One is considering the function from this space, where the function vanishes near to the zero, and then the another way is the considering the function on the whole space, but in here we are subtracting from the u the value of the u at the zero. The next is the critical case. Critical case is when the p is exactly equal to n. For critical case, we don't have the previous inequality for any constant. Instead, we have this kind of inequality where we have the logarithmic correction. We have this kind of logarithmic weight. This is known as the Edmonds-Tribbles inequality. Was shown in this work, and its special cases were given in the works of these authors. The constant of this inequality again is the sharp, but this inequality is not scaling invariant because of the +1 in here. So the next we have the scaling invariant version of that inequality, where we have only the logarithm here. The +1 was needed to control the singularity of the logarithm. Even this logarithmic weight just corrects the singularity at the zero, but there is a logarithmic singularity arises on the surface of the ball. To control that, they added 1 for the scaling invariant version to control the singularity on the surface of the ball. They just consider the function on this domain, which just has compactly support on the unit ball. The constant in here is the sharp and unattainable. The inequality is again now it's in scaling invariant under this scaling, as it's not it's unattainable, meaning there is no extremal function from our space. We have this kind of function, which is the virtual extremizer, and at the same time is the distributional solution for this kind of Euler-Lagrange equation. Here the Cn is the constant, sharp constant of this critical Hardy inequality. The next one is the cylindrical extension of the Hardy inequality, where we just decompose the Rn into 2 parts like this here, and then we consider the distance from the first part only, meaning we have absolute modulo of x prime. That is the distance from the first part. This kind of extension, cylindrical extension, was shown in the work of Badiala and Tarantella. In here, n is between 2 and the capital letter N is between 2 and the small topological dimension n. And when the capital letter N is equal to the small letter n, it just implies the classical Hardy inequality where the constant is sharp. And then they conjecture that for general n also it's sharp, constant is sharp. Then the conjecture will be proven later in the next coming works. The reason for that kind of cylindrical extension was this kind of equation, elliptic equation, which describes the dynamics of galaxies. In here, as we can see, the coefficient here phi is just depends on the r from the first stratum of R3. Okay, the next. I don't have. Okay, the next we have the generalization of the previous inequality, which was given in the first work here. That is when alpha is equal to 1 and the Cauchy-Schwarz inequality is used on the right-hand side, we arrive at the inequality that was given by the Badiala and Tarantella. This inequality is again the sharp. The sharp for the condition alpha is not equal to n over p. Alpha is equal to n over p is the critical case of this inequality. We will just prove the critical case for this inequality in our work. In our work, we use the CP functional, which is this kind of functional, which is non-negative. We use this one to prove to obtain the identities. So the next is the chapter 3, which is the main part of our dissertation. Here we prove the Sobolev-Hard inequalities on cylindrical setting. We have all these results, but we will just show some of the main results from here. The very first result is this kind of inequality, which is the critical case of that last inequality. When alpha, you can see that here alpha is equal to n over p. The constant is in here again sharp and not attained. In the previous inequality, we can see that in critical hard inequalities, usually the logarithmic weight appears on the left-hand side here, but this, unlike them, in this inequality, logarithm appears on the right-hand side. First, this kind of inequality was proven on the homogeneous group in the second work here. We prove it on the cylindrical setting. Then we also prove the identity for this inequality, sharp remainder identity, which helps us to prove the non-attainment of the sharp constant. Then we asked why that logarithm is appearing on the right-hand side. We tried. Then we decided to generalize this inequality and to have this kind of inequality identity with the multiple logarithmic weights. We can see here as now the logarithmic weight is on the both side of the equality. The right hand side here, this integral is the non-negative. That means by dropping it, we can get the generalization of our previous inequality. Here u beta is equal to it just takes these two forms in two cases: beta bigger than 1, beta less than 1. For beta bigger than 1, here this logarithmic weight actually it serves as correction for the singularity at the 0. But there is a singularity at the surface of the ball. That's why we are just subtracting the value of the u on the surface of the ball. Whenever the beta is less than 1, the logarithmic weight will be unable to correct the singularity at the 0, and again there will be the singularity on the surface of the ball, and there is no singularity on the surface of the ball, but the singularity on the origin. To correct it, we consider the function that vanishes near to the 0. Okay, here the a and b just takes these forms. The constant is sharp and non-attained. To prove the non-attained, we just study the sharp remainder term. So by studying the sharp remainder term, we can prove that we cannot attain the equality. In special case, it implies, for example, the first inequality, which is the inequality from the first work. In this case, in this special case, it implies this classical critical hard inequality from the second work, and the last, when we just choose beta and r to be like this, we get our previous inequality with logarithm appearing on the right hand side. Then in the previous inequality, we just consider the beta just except 1. For beta is equal to 1, it's the critical case of the previous inequality where there is actually here, when the beta is equal to 1, there is two singularities, both on the origin and the surface of the ball. To correct that singularities, we consider the iterated logarithmic weight like this here. But again, the problem of the logarithm is that whenever it just even it just corrects the singularity in the previous points, there is a new singularity arises on the new points here. That is r over e and er. To correct them, we just subtract from the u r tilde. U r tilde is takes this form. For this identity actually is again has the sharp remainder term, which is non-negative. By dropping it, we get sharp inequality. with the sharp constant. And by studying the remainder term, we can prove that the inequality is not attained. Okay. Next, by using that identities, actually, we can prove the stability of the extremizers of hard inequalities. What is stability of the extremizer? We don't have actual extremizer, but we have the virtual extremizer. Stability of the extremizer means whenever the inequality approaches the equality, does the function also approach the extremizer? So we prove it by using that our previous identities. Here, this is the classical. This is the hard type inequality. Where we have on the left-hand side here, this is the deficit of the gradient norm, gradient term, and this is the norm of the u. Then this deficit just bounds from above the distance function of u from its extremizer. So whenever this expression goes to zero, meaning the inequality is approaching the equality, then that means the distance function is also approaching zero. That means the function u is approaching its virtual extremizer. So this is the result, is the stability of extremizer. This shows the stability of the extremizer. This one is for subcritical case. For the critical case, actually here, to prove the stability for the subcritical case, we use actually the inequality, critical case of the hard inequality. As you can see here, logarithmic weight is appearing. So to prove the stability for the critical hard inequality, we can see the critical case of the critical case where the logarithmic, just iterated logarithm appears. So here, this is the critical hard inequality. So it just bounds from above. This is the distance function of the u to its extremizer. And also in our work, we proved the higher order inequalities. One of them is this kind of inequality. It's actually a higher order identity. We get this identity from our identity by iterating method. Interestingly, in this kind of identity, we are just we found some Stirling numbers of the second kind. Here, this is the identity mean part, and then this is the remainder terms. Remainder terms all are the positive. So by dropping it, we get the higher order inequality with sharp constant. And by again studying the sharp remainder term, we also prove the non-attainment of the sharp constant. In our remainder term, here the S is the well-known Stirling numbers of the second kind. This actual identity shows the relation between functional inequalities and the combinatorial numbers by just in here the Stirling firstly it was shown in the work of the Scherk here in his dissertation in 1823 that the iteration of the Euler operator like this produces the Stirling numbers whenever we expand the brackets. In our case, we just iterate this kind of operator where for the x we have logarithmic x. For the derivative we have this kind of Euler operator. Iteration of this operator just also produces the Stirling numbers of the second kind. Interesting fact for this identity is that also we can easily by choosing the sum of the for some special functions, we can show the relations between the combinatorial numbers. For example, if we consider there's a problem. Oh, okay, sorry. Yes. For example, by just considering this kind of function, an exponential function, where the t is the logarithmic weight, we get this kind of identity. In this identity, the 2 mu factorial is coming from the gradient term, and then this is the from the LP norm of comes from the LP norm of the u, and then this is the remainder term. all of them are positive, this identity just gives us exact decomposition of the difference of the factorial 2 mu factorial and the square of the double factorial. And also, by considering some other functions, we can get some other identities for combinatorial numbers. The next, we just generalize our previous inequalities for this kind of inequality, where we have general weights. In this inequality, we have this kind of function phi. By choosing the phi for just some functions that just satisfies this condition, we get our previous inequalities. Even we can get some other well-known Hardy type inequalities. Here, the W is this kind of weight function, and the V is in here this kind of weight function. And then, in its special case, it implies, for example, this kind of, along with other Hardy type, classical Hardy type inequalities, it also implies this kind of some non-standard inequalities, like, for example, Agmon type exponential Hardy-Poincare inequality, where we consider phi to be exponential function like this, and then we can see easily that it just satisfies our condition. Then it also produces the weights like W and V in here, ending in the inequality like here. Again, in this here, as our previous inequality with general weights are sharp, this inequality is also the sharp. So also one of the interesting results is that it also produces anisotropic weights, where the weight is direction dependent. Usually in Hardy type inequalities, weights are radial, meaning they don't depend on direction. But in this kind of, if we just consider the phi to be this kind of weight, where the A is the symmetric positive definite matrix, we just get this kind of inequality where the weights depend on direction. We can easily see that by just choosing some special matrix for A, for example. If it's diagonal matrix 2, 1, then we can see that that weight is direction dependent. On the next, we have chapter 4. In chapter 4, actually, we proved our results from the cylindrical setting, analogous of them on the stratified groups. On the stratified groups, we just consider, instead of the Euler operator like this, we consider the horizontal gradient, where we have the left invariant vector fields that just takes this form. And then just again, so exactly we will have that inequalities on the stratified group with this horizontal gradient. So for homogeneous groups on the chapter 5, we just get our inequalities analogs of them on the homogeneous group, where we just consider any homogeneous quasi-norm. And also we just consider the radial derivative like this. So in here, in our inequality, Euler operator is replaced by this radial derivative multiplied by distance. The next is application. The last chapter is in here. In the last chapter we proved that we have 3 subsections where we prove Caffarelli-Corrin-Nierenberg type inequalities, which is the more general inequality, and then also we proved the logarithmic function inequalities. It's log-Sobolev type inequalities, and the last we proved we use our inequalities for proving non-existence of general solutions for parabolic equations. First, in the first chapter of the last chapter, chapter 6, we proved Caffarelli-Corrin-Nierenberg inequality, which is more general, and in its special case, for example, when the delta is equal to 1, we get our very first inequality, and then in here it's constant. Is in special cases it's also sharp. This inequality, Kaffer-Eckert inequality, implies in the special cases this kind of inequalities, which is called uncertainty type principle, uncertainty type inequalities. In the special case, we have this kind of inequality, which can be considered as a critical case of classical Heisenberg polynomial uncertainty type inequality, like this in here. You can see here n cannot be equal to 2. N is equal to 2 is this critical case. So our inequality here is the critical case of uncertainty type principle. In the next subsection, we just prove Sobolev type inequalities, log Sobolev type inequalities. Among them, we have this one, for example, weighted log Sobolev inequality, where we use the log Hölder inequality and the cylindrical Hardy-Sobolev inequality. And here, in this special case, when s is equal to 0, it implies this log Sobolev inequality from this work. Also, we have logarithmic Hardy inequality. Again, also we just cylindrical extend the log Hardy inequality from this work. So when the capital letter N is equal to the small letter n, we have the result from this work, which is the logarithmic Hardy inequality. Then also we prove the log Sobolev inequalities on the on Gaussian measure. Here we have gross type inequality where the constant doesn't depend on dimension, and we have Gaussian measure. Actually, as we are considering the cylindrical setting, our Gaussian measure also is decomposed, and it's the Gaussian measure of the first part of the Rn only. So mu here is decomposed to mu1 and mu2. Here mu1 is the Gaussian measure, and the mu2 is the standard Lebesgue measure. Okay. So the last is the applying our inequality for the parabolic equations. We just apply our inequality with general weights to this kind of equation where we have just general weights v and w tilde. We just give some conditions for v and tilde to be we just show by using our equations inequalities. We show that for which cases this equation doesn't have generalized positive local solution. So whenever this Rayleigh equation is equal to minus infinity, our equation doesn't have a positive solution. For special weights, for example, we get for the v and w. If we choose special weights, we get this kind of inequality. Corresponding equation will just take this form. Here, from the condition for general weights, we can it implies the condition for the constant in this equation. Whenever the constant is bigger than the sharp constant of the critical Hardy inequality, this equation doesn't have positive local solution. The next is also we are applying this kind of inequality and proving this kind of equation where again the constant, if it's bigger than the sharp constant of the Hardy inequality, then this equation doesn't have positive local solution. The last one is the geometric Hardy inequality, which we have where we have the distance function distance to the boundary. Again, for this inequality, we have this kind of equation where this constant is bigger than the sharp constant of the Hardy inequality. Then this equation doesn't have positive local solution. So in conclusion, we just develop a systematic framework for cylindrical Hardy type inequalities. We derive higher order identities, and also we obtain we generalize our inequalities to general weights, which show how to construct the general weights. And then we also just prove the cylindrical inequalities on the groups the stratified groups and the homogeneous groups. And also we use our inequalities for Caffarel-Konner inequalities, Log-Sobolev inequalities, and for proving the non-existence of solutions for parabolic equations. And as a future directions, we can just say to study the applications of inequalities for the in the PDE, like the existence and uniqueness of blow-up, and also analyze the critical limits, and also show and also study the attainment and stability, and also just try to prove these inequalities on the more general settings like metric measure space, or like Cartan-Hadamard manifolds, and also the fractional analogs, and also the some applications of our inequalities for more general inequalities. Thank you for your attention. Yeah.
Okay. Thank you very much for your presentation. So now I will allow each of the committee members to ask some questions about the PhD work. So can I start with Professor Takahashi?
Yes.
Can you
Can you hear me?
I
Yes,
can hear you, yes.
Yes. Thank you very much for nice presentation. Okay, my question is about the last part of your non-existence of parabolic equations with singular potentials. So do you have some existence result for such parabolic equations, local solutions?
Yes, for existence, actually, we don't have one now, but it is the one of our plans.
Yeah. Maybe if the constant C is strictly less than some critical number,
Yes,
you
yeah,
can guess that's the existence of.
yeah.
Yes,
Actually,
C is.
yeah. In the usual application of hard inequalities, yeah, whenever the C is less than the sharp constant,
Yes.
yes, there is existence.
Yes, maybe the result by Barras and Pierre or something like that.
Yes, Barat-Goldstein, yeah.
Barras, yes, Barras. Okay. So this is a future plan for you.
Yeah. Yes.
Yeah.
Yes. Thank you for question.
Okay. Thank you.
Thank you. No further questions?
I have a question concerning the stability result. Can you show it again?
Yeah, actually, yes, here.
So we see the extremal function is not LP, yes?
Yes.
And you use the weight. And you said about the applications of the inequalities and the identities. But what are possible applications of the stability results? I have no ideas.
Actually, yeah, I have heard some the stability as a term in the PDE, but they have the different meanings. I don't know, maybe it's about the stability of the solution for the corresponding PDEs, possibly. I'm not sure about that.
So there might exist rigidity results for solutions, maybe. That's interesting. Okay, thank you.
Thank you.
Okay, thank you. Can I ask Professor Meshki to ask your questions?
Okay, thank you. So, in fact, I would like to once more just to come to the method of identity-based approach. I mean that what is the preference of this approach regarding with respect to traditional methods? I mean that why it was necessary to use such an approach. I mean.
Okay, thank you for question, Professor. Actually, it helps us. We use a functional CP, which is non-negative, and then it helps us to study the attainment of the extremizer. So whenever we have, for example, this kind of identity, just we study the when the CP functional vanishes. So there is a lower bound for the CP functional, and then by studying that inequality, we can see that CP vanishes exactly when the B in here is equal to 0. So when this B is equal to 0, and then that B is equal to 0 whenever the U beta is equal to of this kind of profile. So again, that is the virtual extremizer. And as that virtual extremizer doesn't belong to our functional space, we say that the sharp constant is non-attained. Yeah, yes.
Okay, thank you.
Thank you very much.
Okay. Have you further questions? If not, then we go to the next Professor Zayhum.
Хорошо.
Okay,
have you
can you hear me, Yerkin? Yes.
Yes, yes, person, I can hear you.
Yerkin, it was a nice presentation. I have some couple of questions. The first question is, you in your inequalities, this logarithmic weight appears. I want to ask, is this logarithmic weight optimal, or can you replace this weight by maybe a slowly, growing function?
122.
Yes. Okay, actually, yes, logarithmic weight, actually, we didn't study that if it's optimal or not, but as I know, some literatures there, like the Professor Megumi Sano, in where she proves the if we consider, for example, in her work, she takes a general weight like here, and at the end she proves that it's natural that the weight to be logarithmic.
Okay, because in some of your inequalities, you have iterated logarithm, so 2 times logarithm. So,
Yes.
The next question is related to this one. So, we stop at 2, or we can maybe proceed with this iteration to obtain more refinements.
Yes, there are actually some works related to that where the logarithmic weight just infinitely actually can be iterated like that. For example, in each step, it just for example, we're here. For example, if the exponent of this iterated logarithm, if it's equal to 1, in its exponent is now it's not 1, it's p. If it's equal to 1, then it will be unable to just again correct the singularities at these points. Then for the correction of that, we will have to just consider 3 iterated logarithms. So we can continue, but whenever for that, there are some results where the result of the Geshtezi, I think, Geshtezi, where he considers the iterated logarithm, but he considers the ball. And as iteration of logarithm just increases, then the radius of the ball just also decreases because of this new coming singularities. Yeah.
Okay.
So
Okay. One last question. This is about you have some results in which your extremizers are virtual; they are not attained. So, have you thought about enlarging the function space instead of LP so that your extremizers, this virtual extremizer, becomes extremizers in this direction?
Yeah, I have heard some works related to that, where the author just again considers some larger space to have attainment. Unfortunately, but I didn't study. I didn't go to that direction yet. Maybe in the future.
Thank you very much. Thank you.
Okay, thank you for your questions. Can I now ask Professor Kalibay to ask your questions?
So, first of all, I'd like to mention that I look through the revised version of the dissertation. And 2 points that I raised in my report have been clarified in the new version, so I have no further comments on them. So, and my question is about sharp reminder identities. No, as for sharp constant, yes, it has applications. And for example, in my own research, sharp constant can be used to obtain positivity of some functional. Then this positivity of functional by variational method can be applied, for example, to non-oscillation result and so on. No, sharp constant, yes, and you already mentioned, yes. So, but what about reminder identities, sharp reminder identities? Could you explain what the reminder terms adds from the point of view of application? Does it give some new information beyond the sharp constant, or its
Yes.
main role to explain non-attainability?
Yes. For now, we didn't study that yet, but there is a idea that as we are just in this from the last parabolic equation, we can see actually we study the Rayleigh quotient like this one to prove the non-existence. Here, U tilde actually is W itself is the standard weight of the Hardy type inequality. U tilde means it's multiplied with the constant less than 1, meaning it just decreases its sharp constant. So I'm thinking maybe if we just consider the identity instead of the inequality, so maybe there will be just some extra terms can arise somewhere here, but and also in the corresponding equation, but I'm not sure. In the future, maybe we will study it.
Okay. Thank you.
Thank you, Professor.
So I don't have any other questions.
Thank you for your question. Can I now ask Professor Aripova to ask your questions?
Да, у меня имеются вопросы. Я бы хотела задать на русском языке вопросы. Первый вопрос такой. Например, можете открыть тот слайд, там, где написано связанные там с группами ли? Это в начале. В самом начале это название как бы тем, что ли. Да, вот 3.
Okay. Content, yeah?
Да, вот, например, смотрим, да, Соболев, Харди, неравенство и identities on stratified Lie groups, да? Как понять, вот, например, в этом смысле именно элементами группы Ли, что являются по вашей диссертации? Вот это у вас какой пункт? 1, 2, 3, 4, да? Соболев, Харди, type inequalities and identities on stratified Lie groups.
Yeah.
Кто являются элементами группы Ли?
Yes, Professor, let me translate then. She's asking in the chapter 4 and 6, you consider your inequalities and Lie groups, stratified and homogeneous. So she's asking what are the elements of the Lie groups in your results. So as we mentioned, we just consider the analogs. We just showed analogs of inequalities on stratified groups, where we just use, instead of the standard gradient, we use the horizontal gradient. So the horizontal gradient is the element for stratified groups, and then for homogeneous groups, why we can get that inequality, because if we just apply the horizontal gradient for this distance function, so we get exactly the same result as in the Euclidean case. Also, the divergence works in the similar way. That's why we get inequality in the stratified group. For homogeneous group, we consider the radial derivative with respect to this homogeneous quasi-norm quasi-norm, and then so that are the we can say the elements in the homogeneous Lie group. So we just replace the Euler operator with the radial derivative with respect to r multiplied by this modulo x. Yeah.
То есть, например, смотрите, в механике есть скобки Пуассона. Там как бы есть функции. Эти функции, скобки Пуассона, они удовлетворяют как бы условиям группы Ли, да? Точно так же, ну, если сравнить с тем, то есть вы здесь хотите сказать, что элементами для вашего доклада, элементами группы Ли являются градиенты, а не функции, да? Или как
Yeah,
понять?
the function, yeah.
Обыкновенная. The usual Euclidean space is our group, but we have one extra multiplication Lie structure.
Нет, должны же быть элементы. Элементы — это числа, или же функции, или же операторы. Что являются?
Okay, so it's the usual Rn. Actually, the professor is again asking what are the, for example, elements. So we can say the the domain is Rn with the group structures. Okay.
Окей, хорошо. И следующий вопрос. Например, вы там получаете неравенство с какими-то весами. Weighted, да? Если убрать вот эти весы,
Yes.
что у вас будут? Как думаете, какие результаты будут, если все это рассмотреть без весов?
Yeah, yes. Okay, so the professor is asking what happens if you just drop the weights? Can you have the inequality without weights? Actually, yeah, all of this again started from the very first slide where we mentioned the Sobolev type inequality. So it was firstly given in the work of the two Japanese mathematicians, where they replaced the gradient in the Sobolev inequality with Euler operator. So without weights, actually, it gives this kind of Sobolev type inequality. Yeah. So it builds on this inequality. Yeah.
И потом вы, если не ошибаюсь, получали generalized solutions, да?
Yeah.
Обобщенные решения, да? То есть вы получаете обобщенное решение, а что помешало получить классическое решение?
Yes, the professor is asking, you are just obtaining the generalized solution in your application to the PDE. Actually, we just proved the non-existence of the generalized positive local solution. So there is no positive local solution, generalized positive local solution. Okay, let me go to that slide. Yeah, here there is no generalized positive local solution. Yeah, so there is a definition for generalized positive local solution, where we just weaken some conditions on the solution. So then we call it generalized.
Хорошо, у меня больше нет вопросов.
Okay, thank you for your question.
Okay, so thank you for your questions. Can I now ask Professor Ismailov to ask your questions?
Yeah, thank you. In fact, I asked all my interest question last time, but anyway, here I have some kind of general question. So you are studying all the identities and inequalities on stratified Lie groups and the homogeneous Lie groups. I'm just wondering that how essential is the homogeneous structure of Lie groups? I mean, can these results extend to other types of Lie groups? For example, if you consider some nilpotent Lie groups which are not homogeneous, or maybe some solvable groups. So I mean, how essential is the homogeneous structure of Lie groups in your work? Yeah.
Yeah, we have actually some results related Hardy type inequalities that was obtained in the like gradient groups, nilpotent groups in the works of our my supervisors. But for now, we didn't just consider some other groups. Maybe possibly, yeah, possibly also we can also see we have seen some results on Cartan Hadamard manifolds. I think that also these results can be extended for that groups as well.
Okay, thank you.
Yeah.
Okay, thank you
No more
for
question.
your question. Can I now ask Professor Kadyrov to ask your questions?
Okay, thank you. So you mentioned Stirling numbers and the other combinatorial numbers appear in your thesis. Can you elaborate how they appear in your case?
Yeah, again, here, let me go. Yeah, so here the first identity we obtained was sharp remainder formula for our very first inequality, where we have the where we have the mu is equal to 1 version of this inequality. So we are just first we get we start from the mu is equal to 1 version of this identity, and we just iterate. We just replace the u with the log function multiplied by the x gradient of the u. So we do some calculations, we just expand the brackets, and then we get the second order, and then to obtain the third order, we again replace the u with the log times Euler operator of the u, and then by just doing this iteration, we get the higher order version. So interestingly, in the every time we just when we do the iteration, we get the remainder terms on the right hand side. Interestingly, they are all positive. Again, inside the remainder terms, inside the norms, we get these Stirling numbers. They were produced by the iteration of this operator. This one is actually the iteration of this Euler operator is just that it produces the Stirling number was shown in this work even in 1823. But in our case, instead of the x here, the logarithmic weight we have, instead of the derivative, we have this Euler operator. So we can say that this is the kind of the multidimensional version of this identity.
Next question is more related to Nurlan Ismail's question. So about extension of your work. So it looks like you are using dilations, and it looks like it's crucial. Dilation is an automorphism, and for general Lie groups, I think we don't have this kind of dilation. So that might be one limitation if you want to extend. So my question is, are there any other limitations, weaknesses of your method to extend?
Actually, I'm not sure about this, as we didn't study it in other groups apart from the homogeneous and stratified groups. But for the future plan, I'm just planning to study to try to extend it to some other general settings. For now, I don't see. I'm not sure about if it has any limitations or not.
But okay, but what would be the next thing to try beyond homogeneous case?
Yes, as we mentioned already, again, there are some. We can see there's some related results obtained in the Cartan Hadamard manifolds. Maybe possibly yes, to extend to that manifold.
I see. Okay. No other questions.
Okay.
Okay. Thank you for your question. Can I now ask Professor Derbikov to ask your question?
Really, I have no questions, but I'm thinking about this homogeneous structure and nilpotent stratified structure. So because we have on the Carnot group we have a homogeneous structure, so really it means that the Carnot groups unite both your approaches, nilpotent stratified case and homogeneous case. And it is interesting whether, so really on the nilpotent case, we have more tools. We have left invariant vector fields and something like this. But the homogeneous structure is not so beautiful like a nilpotent structure. So it would be interesting to compare the results, say, whether the results for nilpotent groups, for Carnot groups, if you will consider them simply as homogeneous groups, are they the same? Or maybe this nilpotent structure gives you something more. It's interesting for me.
Yeah, maybe in the future, as a next work, we will consider. Thank you for your suggestion.
And also, I think if you consider the cylindrical case, it means that looking at homogeneous groups, we must consider the product structures when we say multiply a homogeneous group by, say, a nilpotent group. So we will have some product structures, and this will resemble your cylindrical case, I think so. So this is simply a comment, not a question.
Thank you very much. Thank you.
Okay, thank you for your questions. I see that there are also two additional researchers present from Ghent University. So can I ask Dr. Bolis Sabitbek to ask questions, if you have?
Yes, thank you. First of all, it was a very good presentation, and second, that you added this, changed this, put this PG thesis about this Hardy inequalities. That is a very good thing. My question is about these Bessel pairs. Is it possible to get results on logarithmic Hardy type inequalities using Bessel pairs?
Yes, actually, usually the Bessel pairs produces implies in special case many well-known Hardy inequalities, including the critical cases also. In our inequality, our weights are actually they're equivalent to Bessel pairs. Yeah. So we get
but I mean like this kind of logarithmic type. Can you get some log term on these weights?
Yes, we can get.
Okay.
So I don't see if we have. I didn't put it in here, but in the dissertation, I think we have it.
Okay. Thank you. That's all.
Thank you very much.
Thank you. Dr. Erkin Karimov, do you have questions?
Yes, my question is a continuation of Professor Kadirov's first question, namely these special numbers, Stirling numbers and other numbers appeared because of the iteration of Euler operator.
Yes.
And I'm wondering if you replace the Euler operator with more general, for example, fractional, Bessel, or hyperelliptic operators, what kind of special number sequences or special functions do you expect to see instead of these Stirling numbers or the numbers what appeared here?
Yeah, actually, there was a plan. Actually, we couldn't do finalize. We couldn't do it yet. But we were wondering if to consider the, for example, the critical case of the relief inequalities, where we have actually the Laplace operator. I'm not sure, but yeah, for sure, the iteration in the higher order cases, there will appear some sequence of numbers, but will they be some well-known commutative numbers or not? I'm not sure. In our case, so interestingly, these Stirling numbers appeared. We didn't know that it will appear, but there was, but during the iteration, some numbers appeared. Then we just typed it in the Google. Then it appeared to be just that well-known Stirling numbers of second kind. For other operators, yeah, maybe, possibly, yeah, we can get some sequence of some other numbers. But will they be something new or something related to classical numbers or not? I'm not sure yet.
Thank you very much. I have no more questions.
Okay, thank you. Are there at this stage additional questions among the committee members? The committee is large, so maybe we don't go for a second round, but if there are additional questions among the committee members, these can always be asked at this stage.
I think so. You can ask. I think.
Well, I'm not in the committee. Can I ask a couple of questions?
Yes. Anyhow, I was planning to give also the rest present to give the opportunity. So
sure.
if there are, okay. So I see there are maybe not of committee members, but in fact also, because I don't know everyone additionally present here, but anyhow, additional people present here can also ask questions. So please, the person who started the discussion, please proceed with your questions.
Sure, thank you. Nice presentation, thank you. I'm not expert in this area, but like my question is like, I see that you divided for the strata and the singularity is happening in the first strata. Can you replace like the Rn in the second part with the compact region?
The functional space?
Yeah, like here, like you see, like you split it like Rn into two parts. Like what if I have a, like basically Rn with like, let's say circle or some compact region? Like, can I still run your method?
Instead of this first part, you mean, yeah?
Yeah, the first part I leave it, but for the second part I will have some compact region.
Okay. Yeah, maybe, yeah, possibly, yeah, we can get it. Actually, this the second part doesn't play much role in here. We asked the function to be compactly supported in the whole Rn. So if we just put the necessary conditions for functional space, maybe possibly, yeah, we can get it for that domain as well.
I see. The second question is like, how much, for example, like when I split it for the stratas, like, does it depend on the singularity, like which strata singularity is happening? Like,
yeah, this as we are considering the distance from the first stratum, the singularity is happening in the first stratum only. Yeah, there's a singularity in the first stratum. Yeah,
I see. Yes, thank you. That's it. Like, I don't have any question.
Okay, thank you for your questions. Are there additional questions of the people present here?
Тоже имеется один вопрос. Вы здесь рассмотрели параболическое уравнение, да? У вас в уравнении коэффициенты постоянные или переменные?
Coefficient, yeah, professor is asking, you are just considering the parabolic equation here. In your parabolic equation, the other coefficients are constants or the variables. If I understood you right, you mean this constant here, yeah? This coefficient here. This coefficient is actually the constant here.
Окей, хорошо.
This is the constant that is closely related to the constant, sharp constant of our inequality. So whenever it's big, it's doesn't have solution.
То есть, если там будет коэффициент переменной, это уже дальнейшие исследования, верно?
Then I think that is a professor is asking what if the coefficient is some variable or function. So I think that is some that goes for some other directions. I'm not sure about that. Possibly it will not be related to this to our hard inequalities then. Thank you.
Thank you.
Okay, thank you for your question. Are there additional questions?
I think no questions from our side.
Okay. No further questions. If there are no further questions, then we can end the question and answer part of the public defense. And now we go over to I will present the official reviewers report, the official scientific consultants reports, and the official reviewers reports. So let me start with the consultants report, scientific consult reports of Yerkin of Nurgisa, which was one of the supervisors of the candidate. So he writes, the dissertation, cylindrical and subelliptic Sobolev-Hardy type inequalities is a completed scientific qualification work containing new and significant results in functional inequalities and their applications to PDE. It meets the requirement for the degree of Doctor of Philosophy, PhD in Mathematics, 5D05402 at SDU University, and for the degree of Doctor of Science in Mathematics at Ghent University within the framework of a joint doctoral program between SDU University and Ghent University. I recommend the dissertation for defense. So this is the scientific consultants report of Professor Nurgisa. Let me also read the...
Excuse me, I'm here participating. If I may, can I add a couple of things?
Yes, you can, certainly.
Yeah. Okay. So, dear chairs, dear members of the committee, dear colleagues. So first of all, I'd like to thank committee members for taking the time to read, to review, and evaluate Yerkin's PhD thesis. So let me briefly explain the main idea behind of this research. So idea goes back to works by Japanese mathematicians Ozawa and Sasaki. So they asked the following question: if we take classical Sobolev inequality, then we have the gradient operators. And question is, what if we replace this gradient with Euler operator, which has many interesting and nice properties. For example, Euler operator is homogeneous operator of degree 0, and this is natural generator of dilations. And then also independently, this question was investigated by Balinsky, Evans, Lewis, and Hundermark. Then it turned out that to have such inequality, then there is a criteria. So one can have it only when Q equals P. Then we, in our earlier joint work with Michael and Durwood Khan, we developed further these results. And using this Euler operator, we constructed new operator which admits fractional powers. So fractional powers in the sense of Balakrishnan operator. Then using this, once we have this fractional power, all nice properties, then natural question was to develop this embedding results. Because, when we work on, especially on general Lie groups, there we don't have we don't have no invariant homogeneous differential operator. So we have the differential, but it is not homogeneous invariant hyperelliptic differential operator. But it turned out that it is possible to work with Euler operator or radial derivative operator. Then, when we developed this theory, there appeared critical cases. And it turned out that in the critical case, of course, it was expected appearance of logarithm, like in the classical case. But what was unexpected is the logarithm term appeared on the side where we have differential operator. Usually, if you check this classical results, then logarithm term usually appears where we have function. And then in our case, this logarithm term appeared on the side where we have differential operator. Then now Yerkin's thesis now explain us. So this reason of this appearance was left. Then now Yerkin's thesis explains this phenomenon by providing more general framework. And I think that second important contribution is it's about identities. So here we have not just inequalities, but identities. Identities give many useful information. For example, of course, before I should say that before there were identities, especially in the case of L2. But in the case of LP, there were identities, but for real valued functions. So in Yerkin's thesis, what is new is he has many useful identities for complex valued functions. So first, this approach was probably started by Laptev and with his co-authors. So where he and with his co-authors introduced identities for magnetic function inequalities. So now this Yerkin's thesis continues this direction, now not just for magnetic, but now for many classical function inequalities, we can have identities for complex valued functions and in more general LP setting. Okay, and of course identities, since there are non-negative terms, dropping them, we can obtain corresponding classical function inequalities. So one can refer to these inequalities as improvement of classical function inequalities. And it turned out that when we have this kind of equalities, then it gives us information about extremizers. Usually, to investigate extremizers, people use these heavy variational methods. So variational methods are complicated usually, and there is no universal approach. So it turned out that if you have this kind of inequalities, then it's easier to investigate properties of extremizers. Here, yes, in the case of Hardy, we investigated here virtual extremizers. But we also have other works, but we didn't include it here for Poincare inequality, where extremizers exist, and the same type of identities can be obtained. And using these identities, one can investigate properties of extremizers. And another application of this identity, Yerkin showed here stability type results. Stability it's again another information about extremizers. There were questions about applications of stability. So first of all, this is interesting itself. It gives now much more information about inequality, if inequality is stable and so on. And also, since we all know that this kind of inequalities are usually useful in studying appropriate estimates for linear or nonlinear PDEs. Also, since we have here hard inequality, so it means it allows us to investigate with singular potential PDEs. So then, since this extremizer is related to the solution of corresponding PDEs, so it means it gives us much more information about the property of the solution. And another application, what we use it, but not in this thesis, but we didn't include these results because we knew, as you see, that thesis already contains 260 pages. So we thought it's too much if you add here. The another thing is when we have stability, then it can give us information about eigenvalue property. It gives us lower bound for first eigenvalue, or sometimes it gives us information about spectral gap, which is by gap I mean the first and the between first and the second eigenvalue. And there is an interesting question by Yao, so-called Yao's conjecture, which was about spectral gap for usual Laplace operator. So it turned out that this kind of research also useful in studying now for LP. So for P Laplacian, one can study now spectral gap for P Laplacian, which is still open question. But now using this kind of identities, it gives us some estimates from below for spectral gap. So there are this kind of applications. Also, there are many other applications. So I'm just listing what we worked. Then, if I say about setting these techniques here, turned out that more general as a method, then so since these results can be, since methods are more general, so it can be extended to more general settings like cylindrical, stratified Lie groups, or homogeneous Lie groups. About cylindrical setting, this what gives novelty is the following. So usually if you consider classical inequality, then singularity appears at one point. Now in the case of cylindrical, now singularity can lie along whole line, whole axis, or a whole this lower dimensional some subspace. So it's not necessary to be just one point now. If I say about in the setting of the Lie groups, then of course it is very well-known fact that there is a Heisenberg group, right? Heisenberg group is subclass of stratified or homogeneous Lie groups. And this Heisenberg group is very well-known prototype of Sub-Riemannian setting. So Yerkin's thesis connects this geometry, analysis, and also PD, right? Because Yerkin showed in his last chapter, if I'm not mistaken, applications to nonlinear parabolic equations with singular potentials. Okay? If I say about Yerkin, so recently, only very recently, Yerkin obtained a research grant of Kazakhstan for 3 years. For this research, I think this proves he's as an independent researcher. So overall, I think that this thesis contains substantial and original results and fully deserves the award of PhD degree. Thanks.
Okay, thank you very much. Can I now also ask the other scientific consult, namely Supervisor Michael Rosansky, to present your consultant's report? Or
Yes.
have additional remarks or comments?
Okay, so I didn't prepare a special report, but I'm happy to contribute my remarks and comments.
Yes.
Of course, Nurgas has already put this Yerkin's research into a good perspective. And let me just say that in this PhD thesis, Yerkin has done very comprehensive analysis of cylindrical inequalities. There was nothing about that to the extent that he analyzed. And I should say that he basically obtained best possible results, because identities, not just inequalities, but identities. The identities have a big advantage because they contain a lot of information. They contain information about extremizers. There is research on stability of function inequalities. One can use these identities to show stability. There is another independent big direction of research in proved hard inequalities, for example, and where one tries to find second term in this inequality, but again, identity could be used for that. So it is, I would say, the best possible results, and it's also very surprising that there is a link with combinatorics, because Stirling numbers, long numbers, and other combinatorial numbers appear. As he has shown, one can use these inequalities to obtain relations between combinatorial numbers. So this is also interesting observation. And I would say that hard inequalities have been around for more than 100 years. And as some of you know, a few years ago, Suragan and I wrote a whole book on this, 600 pages of new inequalities. And Erkin's work provides yet more inequalities about this topic. So I think that it's a very solid, comprehensive piece of work, and in my opinion, it certainly deserves a degree of PhD degree. So thank you.
Okay, thank you very much. Now we go over to the presentation of the official reviewers' reports. So can I ask first the first official reviewer, Professor Futoshi Takahashi, to give a to present your report?
Yes. Do you hear me?
I hear you. Yes, we can hear you. Sorry.
Okay. So in my report, I am very positive for the dissertation of the Yerkin, because the result is very plenty enough, and dissertation is over 200 papers, 200 pages, and also it contains many results, many new results, and interesting. And technically, it's very rich in reasons. So one point that I have to point out is of course, in the future, maybe the Yerkin must be independent of the group now he is belonging to. So I think that his future success, I hope his future success. But now I'm very positive for his PhD thesis. That's all.
Okay, thank you very much for presenting your report. Can I also ask the other official reviewer, Professor Alexander Meshki, to present your report?
Thank you. So it was very detailed, characterized the results of the thesis. I will not go to the details. My report is positive, and I would like to just to mention the conclusion. Okay. So I will read some places from my report. So the scholarly quality of the doctoral candidates' publications is consistent with the subject of the dissertation. The published and submitted papers substantiate the principal findings of the thesis and demonstrate the advancement of the theory of cylindrical and subelliptic Sobolev-Hardy type inequalities. So so it should be underlined also so applications of the derived results, and so one of the chapter it is dedicated to applications. So the dissertation fully satisfies the requirements for the award of the PhD degree, and I fully recommend for this thesis and the dissertant to be awarded PhD degree. So this is my conclusion for this thesis. Thank you.
Okay, thank you very much to both of you to present the reviewers' reports. Okay, so according to the schedule, we should now have the general public discussion. So let's open this. So I'm not familiar at Ghent with this, but
Мне вопрос, а в целом, кто что думает о диссертации? Ваше мнение. Хорошо. Сейчас не вопросы и ответы, да, как бы дискуссия. Вот здесь рассмотрели как бы параболическое уравнение, есть ли такие же результаты, как бы результаты по волновому уравнению? Есть такие результаты или такое предстоит исследовать для волнового уравнения?
Yes. Okay.
Как думаете? Это вопрос, но все равно обсуждение, да.
Yes.
Да.
The professor is asking, just giving some comments and asking if there are any application of your results inequalities on the wave equations. Like you are considering the here Kitt equation, but if it's possible to apply for wave equations. Yeah, actually, even in the, for example, the works of the Professor Wolf-Seiwit-Pick, I think there are some results related to wave equations, but we didn't unfortunately consider it to apply it for wave equation, but it should be possible to apply it for just in that kind of equation as well. Yeah.
okay, thank you. Additional points of discussions or questions?
Parabolic equations become elliptic, and is it possible to have maybe more precise results in elliptic case when we have no dynamics? Why this question is not considered?
Yeah, actually,
is not clear.
Yeah, actually, in the beginning. So yeah, so some of our the results, for example, that the very first cylindrical extension of Hardy inequality was considered by the Italian mathematicians Badial and Tarantella, where they considered the non-linear elliptic equations.
Mm-hmm.
That they say that it describes the dynamics of galaxies. Yeah. So they apply the Sobolev-Hardy inequalities in their equation.
Okay, thank you. Other questions or points of discussion?
Лариса Ермузаевна, что думаете насчет работы? Ваше мнение тоже.
Thank you very much for your presentation. I'm so happy to be here to support my former student. I taught him, I don't remember what subject, but I'm not good in this direction. I understand how it is very difficult topics. For example, I am more now work in statistics and probabilities. And I want to tell, but many years ago, 38 years ago, I worked about parabolic equations also. My supervisor was Utilbaev and Kalmenov, now the academics, and I hope Yerkin will be also academic one day because he is very, how to say, I see how he developed. We together at university, how he accurate in his work, how students loved him, and he can administrate. It is very hard way to administrate. To be teacher, it's easy. We take the plans, we teach, but to make scientific work nowadays, to defense for two countries about the so big distance, in Europe and Kazakhstan, joined by internet, I want to say thanks all who did it, organized it. It is the future, but it's future here. It is the at your university. So interesting situation. I'm so happy because Yerkin was my student. Good luck, everyone.
Thank you for
Good health and good interesting result in future.
Мгм.
Thank you very much.
Да, у меня как бы такой вопрос к руководителю и докторанту, да. Ну, например, вы здесь получили результаты для цилиндрической области, но все равно там граница гладкая, да. Но если такие результаты получить, например, для звезды, как бы с острыми углами, будет сложно, да? Верно?
Нет,
Ну, если будет двумерный случай, у вас область будет с острыми углами, да? Ну, звезда, область. У вашей тут Rn же, да? Пусть n будет равно на 2.
Yeah, Professor, let me translate it first. Professor is asking what happens if you just consider the star-shaped domains, yeah? Yeah. Yeah, I don't know, but I have seen some results of inequalities, some non-standard domains, yeah, like maybe possible, but I'm not sure. So,
Мне кажется, у вас, да, область должна быть, какая бы там область ни была, с гладкой границей должно быть, да?
There are also by many Italian statisticians and also here we have also the so together with Michael, also with Dr. Harrison, they also managed to obtain some versions. This kind of inequalities, this kind of amazing. It's not always, but in some domains, with some condition, it is very possible.
Okay.
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 Further questions or points of discussion?
I think that it would be interesting to consider the case in which your singular set is not flat, say not a straight line, but say curve. What are the same type of inequalities, or maybe if we have say a curve in a group, so we have the singular set itself during the nilpotent structure, and it would be interesting how the inequalities will change. So this is, I think it is mainly open and very interesting, but it seems very difficult.
You're right. You're right. You're right.
Okay.
To understand it, we need much time. Much time to understand it. Even definitions.
Теперь мы можем послушать мнение профессора Барта, что он думает насчет диссертации сам, да.
We are wanting to hear your opinion, Bart, about the this dissertation, and what is your advice to vote or don't vote? So, what's your opinion?
You are joking. You're kidding.
Yeah. Well, I'm not in this area, right?
Mhm.
So I'm part of all PhD defenses at Ghent University as chair of the program committee. But let's say that it seems like a lot of work he has done, and it looks like a real nice piece of mathematics he had developed during the last 4 years. So I have no doubts to follow the opinion of the experts who have expressed their opinions already, right? I think I can join their opinion with regard to that.
Okay, thank you.
Thank you.
Okay. Are there further comments or points of discussion?
So we have no comments. I think that's all.
Yeah, that's all. Okay, thank you very much. Does the candidate want to add something to that?
Okay. Thank you, Professor. Actually,
Потом же будет.
Сейчас в дискуссии он тоже может участвовать.
Yeah. Actually, yeah. Thank you for all comments from our dear professors. Yes, there was a lot of ideas and comments, suggestions for the future work. Yeah, for sure. I will just consider them. I will just study, try to get some other results related in that directions. Thank you. Thank you very much. Yeah.
Okay, thank you very much. So now I give the word back to Professor Nuland-Derbikov.
Третья часть. Ага.
Что такое?
Дискуссию закончили. 3.
So we finished the discussion, and I think we must proceed to voting.
Yeah.
And I think we have 2 types of voting, one for Ghent and one
Yes, but
for
we
us.
should have a break, I think, right? In the other, yeah. Or what's the procedure?
Okay, let's make a break for voting.
Yeah. Okay. Thank you. Hello, everybody. Can you hear me? I think you should go to the other room, right?
So we are all here, but non-members leave the room.
No, dear colleagues, I think that all of the voting members should connect to the other Zoom link. I sent the Zoom link,
Okay.
and we should all
okay.
connect to that Zoom link, and there Bart will do the Ghent University procedure of counting votes and so on. So maybe I think please disconnect from here and please find an email I sent a couple of days ago with another Zoom link, and we should all meet there. And there we do the voting, and Bart will summarize the votes, and this is necessary for the Ghent University procedure.
Okay,
So
thank you.
please disconnect here and let me know, but I sent the link.
Okay, I will say the same in Russian. Значит, то, что касается членов комиссии по университету Гента, мы должны проголосовать в другом зуме. И ссылку нам Ружанский уже скидывал, ее надо найти в e-mail и зайти в другой Zoom, да. Ну, да.
Да, всем членам комиссии желательно туда зайти. Там Барт посчитает голоса в соответствии с нашей процедурой.
Так, только надо найти этот mail. Сейчас.
Я могу послать еще раз.
Сейчас надо найти ваш email. Найти надо.
Да. Я сейчас попробую. Я сейчас найду.
Спасибо.
Я пошлю сейчас еще раз.
Вот, я нашел у себя.
Ну нашли тогда.
Я у себя нашел, но другие могут не найти.
Ага, да, сейчас.
Так, митинг, чат, линк.
Как всем послать.
У меня на телефоне-то нету зума. Его надо сейчас все и поставить как-то сюда. Ой, а я что-то про это не подумал.
Я послал еще раз. And Takahashi-san, please connect also to that link. I have sent now another one.
Sorry,
I cannot hear you.
now I have a problem to access the link.
I think you received that link. I sent again. Please connect there, and then you can vote there.
Yes. Now I'm searching.
Okay. Okay. I just sent again just a few seconds ago. But maybe you can find 2 days ago I sent.
Okay.
So, Professor Takahashi, can you?
Okay, yes.
Can go to the other room?
I'm here, but my internet is very unstable now. Do you hear me?
Yes, but you should go to the other room.
I should go to the other room.
Yeah.
How to go to the other room?
Did you get an email from Michael Rosansky?
Yes. I just received Michael's, but this is a long. Which this one? Zoom meeting, no Zoom meeting. This one? No. So in order to vote, I need to go to other room, but I cannot find the link now. I should go to other room. Professor Bloom, do you hear me?
Oh, did Michael send
Yes.
you an email?
Yes.
Please proceed to the other room.
The link once again. Yes, I received the Michael's message, Michael's email, and which this one, but this is a joint. I found only the Zoom link, which is a Zoom meeting, but not for voting, I think.
Michael just sent a link.
This is the link. Okay, voting. Okay, thank you. I find.
So are you connected already to the other room? Is Professor Takahashi, did you already
Yes.
join the other Zoom link?
Yes. Okay. I go to again. Regulation. No.
So it's an email sent by Michael just a few minutes ago.
Yes. Professor, do you hear me? No. Wait a moment. Professor Bruin? Professor Bruin, do you hear me?
Yes, I can hear you.
Okay, okay. And I have voted. Can you check my voting result?
Yeah, well, but it's
You didn't receive it.
yeah, but you should join the other room.
Yes.
Did you join the other room?
Yes, other room. I found a voting link, but how to go to the other? Still difficult. To maybe
SDU rule from Kazakhstan. But currently, you must enter another Zoom.
Other room. Other
Yes,
Zoom.
and you should have an email from Ruzhansky.
Yes,
With
yes.
this new link to Zoom. And
New link to Zoom.
in this new link, we will vote using Ghent rules. So the difficulty that we have two rules, one for Ghent and one
No,
for
this is
Kazakhstan.
SDU. The other is a Ghent rule.
Look at an email.
Yes. I'm looking for Lujansky's email and
Yes, and you must have a link to Zoom.
yes,
New
I
link.
have maybe this one. I'm trying to open, but this is again, this is Kazakhstan's link, no?
Oh, from Ruzhansky, you should have a link to Ghent.
Yes. Could you send, sorry, could you send me again the Ghent room's link? I'm going out from here.
Okay. Can you hear me?
Yes.
Okay,
Yes.
that's fine. So everything's fine. So we're probably waiting for the others. So we should vote in two Google Forms. Where are the forms with these? These forms were, this email was just sent or previously?
I think forms was sent like 15 minutes ago and also 2 minutes ago.
Yeah, but I think I didn't get it. Oh, it's via my Google account, maybe. Sorry. No, it's not there.
So this is the email. I shared the screen.
Yeah.
For example, I didn't get two, so maybe some people get, some people don't.
Yeah. So it was sent like 15 minutes ago and 2 minutes ago, but
I'm sorry. So we have sent the links 3 times, and so we have sent it to the committee members and also to two reviewers. And other yes, they don't have links because they, according to the Kazakhstan rules, they don't have permission to vote. Thank you.
What about Professor Bart de Bruin?
I didn't get it.
So what I see is Bart.
Professor Bart, I have sent you the link to your Ghent email and also to your personal chat in this Zoom account, in this Zoom meeting. Please check
Okay,
it.
yeah.
Thank
So
you.
maybe I'll check this because it can happen that some emails, arrive like with a delay of.
Yeah, it happens. Thank you.
Yeah. Yes, I think I voted. I was able to vote.
Dear Professor Futoshi Takanashi and also Alexandra Meshi, so I have sent you a link to the registration, so in
Okay,
Google Form. So we're waiting for you, and then we will just
I
continue.
see.
You already sent?
I have sent to your personal chat here in Zoom.
In Zoom. Okay, let me see.
Excuse me, we are three who are not in this voting, right?
Yes, you can be free if you want.
Thank you.
So
I registered.
I registered. Yes, I am done.
Yeah, we are ready to continue.
Нет, пока. Ағай, сіз айтасыз, мені председатель қылып жатсаймыз.
Окей, да.
Сосын Исмаиловты как член жаңағы счета қылып сайлаймыз, иә? Олар мені сайлайды, сосын барып анау.
Он не голосовал сейчас.
Исмаилов Нурлан.
Он голосовал за нас сейчас? Нет?
Да, голосовал.
Он не должен голосовать.
Голосовал? Я же голосовала. Почетная комиссияның председатель.
Нет, это я понял. Про Нурлана я имею в виду. Он сейчас голосовал?
Алло.
Нормально?
Лаша.
Окей.
Хо.
Чего?
Все болды, айта беріңіз.
Хо.
Кто там говорит? Okay, we can continue. So we finished our voting. Let me continue. Bart.
Yes.
Okay, so first, according to our procedure, we must have a counting commission, and we must really must have the chair of the counting commission, and I suggest Dr. Gauhar Repova to be the chair of the local counting commission at the SDU University, and we should vote by hands for this, Bart, you too.
Yes.
So, okay, the decision is unanimous. So I will give I suggest Dr. Gauhara Repova say us about the results of our local voting. It's okay?
Болды, иә?
Yeah.
Все, уже кімдерді шақыра береміз и результат шығады. Кірсеңіздер болады. Мен сосын ақыда анау
Гохар.
Да, я уже читаю, да? Ну, этот.
Скажите результаты. So the results of our voting you should see. Okay, please.
Да. Номері бірінші хаттама, есеп комиссиясының құрамы Арепова Гаухар Жұмабаевна, мүшелері Исмаилов Нурлан Аманкелдиевич. Есеп комиссиясы Шаймерденов Еркіннің 8-ді-05-402 математика мамандығы бойынша философия докторы PhD дәрежесін алу үшін Cylindrical and Subelliptic Sobolev Hardy Type Inequalities тақырыбында диссертация қорғау бойынша жасырын дауыс беру нәтижелерін шығару үшін сайланды. Диссертациялық кеңес мүшелерінің құрамы СДУ университеті ректорының номері 1102208 бұйрығымен бекітілген. Диссертациялық кеңестің тұрақты мүшелері 4 адамнан тұрады, уақытша құрамы 3 адам болып бекітілді. Кеңес мәжілісіне 7 кеңес мүшесі, оның ішінде қаралып отырған диссертация саласы бойынша 7 ғылым докторы, немесе ғылым кандидаты, немесе PhD қатысты. Жасырын дауыс беруге 2 ресми рецензенттер қатысты. Олардың дауыстары диссертациялық кеңес мүшелерінің дауыстарына тең. Жасырын дауыс беру электронды форматта өткізілді. Толтырылған электрондық бюллетендердің саны 9, жарамсыз бюллетендер 0. Дауыс беру нәтижесі: философия докторы PhD немесе бейіні бойынша ғылым дәрежені беру 9. Диссертацияны пысықтауға жіберу 0. Диссертацияны қайта қорғауға жіберу 0. Философия докторы PhD немесе бейіні бойынша докторы ғылыми дәрежесін беруден бас тарту 0. Есеп комиссиясының төрағасы Арепова, комиссия мүшелері Исмаилов.
Okay, I will say briefly in English. So she said that all the requirements were fulfilled, and by anonymous voting, the results. So we have eight votes, and all eight confirmed. Okay, 9. Sorry. So of 9, we have 9 positive decisions. That's all. So this is our official report, and I also should say in a report concerning this doctoral meeting, and this doctoral defense meets the requirements for a joint degree under the partnership agreement for the joint PhD between Ghent University and ASD University. The candidate fulfilled all criteria outlined in the agreement, including a public doctoral defense conducted by a joint examination committee approved by both institutions. As a result, the candidate will be awarded a dual degree, earning the titles of Doctor of Science in Mathematics from Ghent University and Doctor of Philosophy from the ESDU University. That's all. Okay, so first of all, we must confirm the results of the electronic voting by hands. So we must vote. Okay, I see.
Доктор Месхи, я ушла к меда, Барт, Талабай, и Камеда үшіншісі. Вот Исмаилов, Шираль ағай.
So,
Все.
it's okay. The decision is unanimous. What's next?
В принципе, ағай болды. Барын жасадық. Енді ген жағынан сөз болса айтсын, немесе соңғы сөз докторантқа.
Okay, we finished our part, but if you want to say something, you could say, and then we will give the final words for the dissertant.
Okay. Well, I don't have so much to say. I would just want to say that I think Ghent University requires a confirmation from SDU University that they agree to award the doctoral degree. And then they will also print the diploma for the candidate. But I think they first need some kind of confirmation that you agree to award a doctoral degree. Okay.
Yerkin?
The results of voting about Ghent University is 100, да?
Yeah. Все проголосовали.
100%, yeah.
Okay. Dear chairs of the examination committee, Professor Bart de Bruin and Professor Nurlanda Erbekov, and all the other members, I just want to thank you for just taking your time and reading my dissertation, evaluating, and also I want to thank the official reviewers, Alexander Miski, Professor Alexander Miski, and Professor Futoshi Takahashi for their official report. And also I want to thank my supervisors, Professor Nurgisa Isirkigen and Professor Michael Różański for their support, for their patience, understanding in throughout all this journey in these 4 years. And also I want to thank the Ghent University for this joint program to happen. And I just I visited Ghent twice, stayed there in 6 months. It's a very beautiful city, and we obtained some of our important results during my stay in there. And also thank all colleagues in the Ghent University and here in SD University who also supported me and also just supported with their assistance in different times. And also, lastly, I want to also thank my family for their also patience and understanding and during my PhD studies here. Thank you all for everything. Yeah, thank you.
Okay, that's all. We finished our agenda today.
Thank you much.
Thank you all the participants from our side, from the Ghent side, and I think we have a good result.
We can.
Okay. See you.
See you. Bye
See
bye.
you. Thank you.
Goodbye.
Congratulations.
Goodbye.
Bye.
Congratulations.
Okay,
Bye-bye.
goodbye. Congratulations.
Все.